All right, in this explainer, we are diving deep into the foundational physics of light. Now, if you're an ophthalmology trainee, listen up because this isn't just some abstract theory. This is the science behind your most important clinical tools, from diagnostics all the way to surgery. So let's get right into it. So let's start with a really interesting question, a paradox, really. We use light to gently image the most delicate parts of the retina, right? But we also use that same light as a high-powered laser, a surgical scalpel. How can one thing be both a camera and a knife? Well, the answer to that is exactly what we're going to unpack today. And the key to solving that puzzle starts with understanding that light has two very different personalities. You could say it has two faces. It acts as both a wave and a particle. And really getting a grip on this concept is, well, it's fundamental. This idea is called wave-particle duality. It's a cornerstone of quantum physics. And the mind-bending part is, it's not that light is either a wave or a particle. Nope. It's somehow both at the exact same time. And depending on what you're doing in the clinic, one of these faces becomes way more important than the other. So what does this dual personality actually mean for you? Let's break it down. On one side, you've got light's wave behavior. This is where things like diffraction come in, and that's what sets the absolute physical limit on the resolution of your imaging. We're talking about your OCT scans, your slit lamp exams, all of it. But then, on the other side, you have its particle behavior. This is all about these tiny, discrete packets of energy called photons. And these little photons, they're what trigger vision in the retina, and they're the microscopic bullets that power your laser treatments. Let's dig into that first point. When light acts as a wave, it naturally bends and spreads out as it passes through an opening. That's diffraction. So what this means for you, in really practical terms, is that no matter how perfect your optics are, this wave behavior creates a sort of fundamental blur. It defines the absolute smallest detail you can possibly resolve when you're looking at the retina. And now for the other side of that coin. When you're performing laser photocoagulation, you're not really thinking about waves. You are harnessing the incredible energy of countless individual photons. Each one of those particles delivers a tiny punch of energy to the tissue. And if you concentrate enough of them in one spot, you can make precise therapeutic burns. So it's simple, right? Waves for looking, particles for treating. Okay, so now that we have a handle on what light is, how do we actually measure its intensity in a way that's useful in the clinic? This isn't quite as straightforward as it sounds because there are two completely different ways to go about it. On one hand, you've got radiometry. Think of this as pure physics. It measures the total, objective energy of all light, whether a human can see it or not. But for you, as a clinician, what really matters is what the patient sees. And that's where photometry comes in. It's specifically calibrated to the sensitivity of the human eye, measuring what we perceive as brightness. It answers the crucial question, how bright does this actually look to my patient? Photometry gives us this really logical sequence to describe the whole experience. So it all starts with luminous flux. That's the total amount of light coming out of a source, measured in lumens. Then you've got illuminance. That's how much of that light is actually landing on a surface, like the retina. We measure that in lux. And finally, the part that really matters to the patient, luminance. That's the actual perceived brightness of that spot on the surface, measured in apostles. So how in the world do we calibrate all of this to human vision? Well, it all comes down to this one single incredibly important number, 555 nanometers. This specific wavelength, which is a kind of yellow-green light, is the absolute peak sensitivity for the human eye in bright conditions. You can think of it as the gold standard. Every other measurement in photometry is weighted against how we perceive this one exact color. Basically, this one wavelength is the anchor that lets us quantify everything we call brightness. And that brings us perfectly to our final section. You see, the light we can perceive is just a tiny, tiny sliver of a much bigger thing called the electromagnetic spectrum. And for ophthalmology, the parts of that spectrum you can't see are often just as important as the parts you can. The eye itself has this brilliant built-in filtering system. First up, the cornea and sclera absorb the most damaging short-wave UV light, that's your UVC and UVB. Then the lens steps in and absorbs the longer-wave UVA, which is a huge part of its protective job. And what does that leave? Well, it leaves mostly visible light and some infrared to pass right on through to the retina. Understanding this selective filtering is just critical for everything from counseling patients on sun damage to ensuring laser safety. And we can use this invisible light to our advantage in some really clever ways. Take optical coherence tomography, OCT.
It uses near-infrared light. Now, why is that so smart? Because it can penetrate deep into the retina to give us those amazing cross-sectional images, all without being visible to the patient and, crucially, without causing any tissue damage. It's a perfect diagnostic tool.
But, and this is a huge but, there's a critical warning that comes with this. While the low-intensity infrared in an OCT is perfectly safe, high-intensity infrared light is a completely different beast. It can penetrate straight to the retina and cause significant thermal damage. We're talking about a real burn. This is a massive concern for laser safety, and it highlights why proper protective eyewear isn't just a suggestion, it's an absolute must. So let's pull all of these threads together. We've looked at what light is, how to measure it in a way that actually matters to a patient, and the full spectrum we have to manage. And remember, these aren't just abstract ideas from a textbook. These are your practical, everyday tools. All right, so to recap, if you just take away 3 things, make it these. First, light's dual nature as both a wave and a particle, that's what makes it both an imaging tool and a surgical laser. Second, understanding photometry is how you measure what actually matters to your patient's vision. And third, knowing the entire electromagnetic spectrum is absolutely critical for both modern diagnostics and for patient safety. Ultimately, whether you're interpreting an OCT, performing laser therapy, or just advising a patient on UV protection, these physics principles are not just academic. They are actively at work in your clinic every single day. They're foundational to being an effective ophthalmologist. And that leaves us with a final thought to chew on. We've mastered these principles to create the incredible tools we have today. So the real question is, as our understanding gets even deeper, what new diagnostic and therapeutic possibilities will this fundamental physics unlock next? What does the future hold?